Okay, hi everybody. We're just going to go ahead and take a look at a couple extra questions this week for the central limit theorem and hypothesis testing. So before we do that, we've got a bit of true or false and multiple choice. So this first question here for the central limit theorem stating that the sample size is sufficiently large, then the sampling distribution of the sample blank is approximately normal, even if the sampled population is not normally distributed. Well, the answer for this one is the mean. Answer for this one is the mean. A sample statistic is an unbiased point estimate of a population parameter if the mean of the populations of all possible values of the sample statistic equals the population parameter. This is true. Basically, if you get equal to the population parameters, then that is a good statistic. The standard deviation of all possible sample proportion increases as the sample size increases. No. Remember, standard deviation measures standard error, right? So if the sample size goes up, your standard error goes down. So this is false. All right. Like the empirical rule, the central limit theorem is only applicable to symmetric distributions. That is false. Central limit theorem can apply to anything and helps normalize the data. If the sample population has a normal distribution, then the sampling distribution of x bar is also normal regardless of the sample size. True, central limit theorem basically guarantees us this. As the sample size blank, the variance of the sampling distribution of x bar blanks. Now, I suggest you actually go through and check out all the possible answers, but ends up being that if you increase this, then the variance of the sampling distribution will decrease. Right, so as you increase the sample size, your variance, which remember, taking the square root of the variance gives you the standard deviation, then that's going to decrease. All right, first question here. What do we got here? A business. Right, so you can take a moment, pause it, and read the question here. And let's take a look here. So, when you're reading through this question, the reason it's a central limit theorem question. So why is it central limit theorem? Well, the main reason is not because we have an n value here of 50. Okay, that just because you have an n value in the question doesn't mean that it's a central limit theorem question. The problem here is that it doesn't say the data is normally distributed. Okay, normally we use central limit theorem for small sample sizes, like when n is less than 30. But if we don't know that it's normal, then that's another time when we use the central limit theorem. So that's the big thing there. And then as far as the numbers go, well, we got x bar here is, they want to know if the probability that it's less than 175. So that's the sample we are testing, and mu is 186.8, and I believe that and standard deviation is 32. There. So I pulled all the information out of the question. Now I can plug it in here, and we are looking for the probability that x is less than 175. So we'll plug it into this formula here. So we got 175 minus the mean divided by standard deviation divided by square root n. Okay, now this is going to give us a z-score. I have some intermediate steps if you like. Should get negative 11.8 in the top and 4.5225 in the bottom. Now when you plug that in, you'll get negative 2.61. Okay, so you can draw your thing here, and here will be z equals negative 2.61. Now, how do I know which way to look? Well, we're doing less than, okay? So that means we're pointing to the left. So you're going to be going and looking up on your z-score table a score of negative 2.61. When you do that, you're going to get, you can go ahead and pause. Should get 0.0045. There you have it. Next question. Okay, now this one here, again, you know we're doing central limit theorem right now. However, you always want to ask yourself, like, how do you know this is a central limit theorem question? So take a moment, pause the video, read the question, and I'm going to go ahead and start writing things out here. Oops. Now in here, it actually says they're normally distributed. Okay, so that's one thing that's like, okay, I don't need the central limit theorem. But then it says if a sample of 25 females are selected. So in our notes, we know that if it's less than 30, it's considered too small and we need to use the central limit theorem. So in this case, that's why we're going to use central limit theorem, and we're looking for an x bar of 128.3 greater than. So we're looking for probability that x is greater than 128.3, and we're going to be using the central limit theorem. So go ahead and write out the formula. And now you can go plug in your numbers. Now I do have a couple intermediate numbers here. So in the numerator you get 2.3. The denominator you get 3.14. So you get a z-score of 0.73. Now don't forget to draw your picture. We have a positive z-score, so we're somewhere over here. Now remember, we are looking for the probability that we are, 128.3 is over here. Looking for the probability that we are greater than that number there. So, greater than is going to be, it's pointing to the right, so you're looking for the area to the right of that there. So when you look up the value in your Z table, you're going to have to go 1 minus whatever answer you get, because remember, your Z table just gives you the area to the left. So we can go ahead and write probability that Z is greater than 0.73 equals 1 minus probability Z is less than 0.73. So this is just saying I'm using the area to the left. And when you go look that up, you're going to get this and 0.2327. Done. Wonderbar. Next question. The good old bacon question. So take a moment to read through, and again, ask yourself, how do we know that this is a central limit theorem question? So we've got the average price of bacon being 2.02 with a standard deviation of 0.08. We have 40 samples, and looking for the probability that x bar is less than $2. So probability that x is less than 2. There. So why is this central limit theorem? Well, again, it's not because we have an n value. That's not a guarantee it's going to be central limit theorem. But again, this question doesn't say that this data is normally distributed. So it's going to be central limit theorem. So we can plug in the numbers. And just got to get my work here. You're going to get negative 1.58. So again, draw your little normal distribution, And here's z equals negative 1.58. Now we're looking for less than, this is x equal 2, we're looking for less than 2, so that's pointing to the left, so we're looking for that area there. So you can go ahead and look that up on your z table. So probability that z is less than negative 1.58, look up that value, you're going to get 0.0571. Another question done. Okay, now this question is going to have a range, and again, as you read it, why is it central limit theorem? So we got a mean score on a dexterity test being 30, standard deviation of 5. The distribution is normal, okay, if it's administered to 22 students. Well, even though it's normal, because n is less than 30, it's a central limit theorem question. So we're going to find the probability that x, so probability that we're between 27 and 31. All right, so that's going to involve doing 2 calculations. These are the numbers we're using over here, and so we can go ahead and yet we're using central limit theorem, and just going to start plugging in my numbers like this. So this is x for one question, that's x for the other. So central limit theorem, we're going to go 27 minus 30 divided by 5 divided by square root 22 less than z less than 31 minus 30 over 5. There. Take a moment to calculate that out. I think I'm just going to jump straight to the answer, so please just pause. And now these are the z scores that we get. Okay, so if you draw this out, so here's the center, and I'll just make this, here's 0.94 for z, and then here's negative 2.81. So when you have an in-between question, you're going to be looking for the area in between those two values. Well, just remember that visually, when you go look up this one, this is going to give you the area all the way to the left, right? Including this little piece here. When you go look up negative 2.81, well, that's going to give you this area. So if you subtract the big blue area, if you take the big blue area and you subtract the green area, you'll be left with just the in-between black area. It kind of makes sense. So basically, if we're going to write this out, we can write probability that z is less than 0.94 subtract probability that z is less than negative 2.81. That's going to equal our answer. Okay, so we can go look up this one. We're going to get 0.8264. And then looking up the other one, there it is. So for a final answer of 0.8239, and we are on our very last question. Now, I wanted to do one hypothesis testing question here. So keep in mind that a lot of these things are on the formula sheet, but these are big questions. There's a lot of work, and you need to certainly practice a lot of these. So I wanted to do one. Now, a couple things here. We got a manufacturer of an over-the-counter heartburn relief medication claims that its product brings relief in less than 3.5 minutes on average. Okay, so when you're doing hypothesis testing, you need to come up with an HO and an HA. Now, the HA is the alternative hypothesis that you're trying to show that there's enough evidence to support it. So you got to look in the question and see, well, what claim are they making? So they're making a claim that their medication is going to bring relief in less than 3.5 minutes. Okay, so that would be our HA. So we're going to say mu is less than 3.5. Now, HO is always the opposite of this, so it's just going to be mu greater than or equal to 3.5. So that's the status quo. Now, the numbers they give us in the question is, they go and they collect some data from 50 heartburn sufferers. So we go n equals 50, and they find that their mean time is equal to 3.3 with a standard deviation of 1.1 minutes. It says assume the time is normally distributed, and then I say part A, test at the 10% level. So in a hypothesis test, what you're trying to do is you're trying to kind of play the probabilities. Okay, your alpha value means that there's basically a 10% chance that you're wrong. So this is a threshold on the normal distribution. Now, if you look at your alternative hypothesis, you see that it's a left-tail test because the less than sign is pointing to the left. So that means your rejection region is right here. We call that Z alpha. Now, on the left-hand side, it's negative, just because the Z scores are negative on that side. But if you land in this area right here that I'm going to shade in, this is where we get to reject the HO. And we need to know what's the Z score for that to happen. So you're going to go look it up on your table. Now, if my memory serves me, I think you get negative 1. Okay, so you're going to get negative 1.28 for the rejection for the Z alpha score. And that's just because you got 90% of the table over here and 10% over here. So you're looking at 0.1 on your Z score. Now, if we fall in this region, this is the region where we will accept HO. It means we don't have quite enough evidence to actually say that the time was less than 3.5. So once you have that all set up, the next thing you're going to want to do is get your Z score statistic. Now, we use the central limit theorem for hypothesis testing. So you can go ahead and plug in your numbers. Now we had 3.3 minus 3.5, and the standard deviation was 1.1 divided by the square root of 50. Now when you go and type that in on your calculator, I'm going to have to do it here. In the numerator, you're going to get negative 0.2. And the denominator, you get this. So when you divide it, you're going to get negative 1.286. Now, the reason I chose to keep one extra decimal, even though there's not a whole lot of point, I kept one extra decimal just to see, because we're very tight here. Okay, so as long as I am going to write here, if Z is less than negative 1.28, we reject HO. Now this is a statement you do need to make. I need to see this, I need to see this, I need to see the picture, I need to see the statement, I need to see this work, and then I need to see you actually make your determination here. So we're going to say since Z equals negative 1.286, and that's less than negative 1.28, we reject HO at the 10% level, and then make a conclusion. So at alpha equal 10%, we have enough evidence to say the medicine took less than 3.5 minutes. Now notice how we don't say that it actually took 3.3 minutes. We don't have enough evidence to say that. In a hypothesis test, you're just showing whether or not you have enough evidence to reject the HO. Now the HO is that it takes more than 3.5. We have enough statistical evidence to just say it took less than 3.5. Okay, so see the slight difference. We can't say it took whatever they found 3.3, but we can say it definitely took less than 3.5. Okay, that's for part A. In part B, I'll just use a different color so it doesn't get too confusing here. But in part B, we're changing the alpha value to 5%. Now, Z alpha, if we look up Z alpha at 5%, you're going to get negative 1.645. Okay, which means that our rejection region moves this way and we can only reject in the blue area or something like that. So negative 1.645. So at the 5% level, this number here clearly is not smaller than negative 1.645. We just say we do not have enough evidence. Oops. Enough evidence to support the claim that the medication takes less than 3.5 minutes. Okay, so thanks for joining me. A couple things to note here. Yeah, make sure you do week 6. That's updated on Moodle, and check my email because there's no top hat. Okay. All right, thanks for joining me. See you next time. Bye-bye.